let's say that our room, this spacecraft, is magically insulated from radiation and heat and all those things. Then nothing. In we would go into the interior. The caveat,
please.
There's a lot of caveats, but one thing I should say is that it matters that description I've given, it's for a supermassive black hole.
Yeah.
If this was a smaller black hole, so smaller, less massive, a few times the mass of the sun, then at some point you experience what's called tidal gravity, tidal forces. So those are the things that raise the tides in the oceans of the Earth. The tidal forces, we will start to, in our freely falling trajectory towards the black hole, at some point you start to feel the tides. You start to get stretched and squashed. And
we feel it.
You'll feel it eventually. You'll really feel it eventually, because formally, as you get very close to the singularity, you get infinitely stretched and squashed. So you really feel it.
I want to talk about that
Spaghettification.
Inside. Yes, that's my favorite.
But so for a smaller black hole, as you approach the horizon, you'll feel those forces. But for the big ones, you don't feel the tides until you've gone into the interior.
So we're moving toward the event horizon. We're somehow insulated from the messiness of the accretion disk. We're moving toward it. I've heard that there's a moment where the physics of this are such that if you and I are actually falling in, if we look to the left and the right, we would actually see the back of our own heads.
Yeah.
Is that anywhere close to correct? And can you tell me about the other little details as we approach the event horizon that you think are important?
Well, one of the biggest details, it's not even a detail, it's one of the most shocking things about this, is I've described this, us falling into the black hole. And we're saying, in this room where we can't see out, what do we feel, what can we measure? And the answer is you can't measure anything and we don't feel anything until we get inside and we approach the singularity for this one. But from the point of view of someone outside, the description is very different. So what would they see happening to us as we fall towards this thing? So even in Einstein's theory, with nothing else, no quantum mechanics or anything, then what they would see is time tick more slowly for us. Mm-hmm. So they would start to see, as we approach the black hole, if they could see our watches, if we were transmitting to them or whatever it is, transmitting from these cameras, we were sending it out to them. They would see our time tick more slowly, more slowly, more slowly, and they would see our time stop on the horizon. So they would never see us fall in. So from the point of view of someone outside, nothing goes into the black hole, ever.
So what, do they see us imprinted there forever, or does the light from us slowly fade until... It
would fade because also you could picture, there are many ways of picturing it, but you could say this light is climbing away from through this gravitational field, so it's getting stretched. So we get redder and redder and redder, redshifted, infinitely redshifted. Time passes more and more slowly until it stops on the horizon when viewed from the outside. From our perspective, we look at our watches, they go at 1 second per second. Mm-hmm. And that's absolutely central. There's nothing weird. Well, there's something weird there, but there isn't according to Einstein. So it's pure Einstein's theory. So that's the first thing to say. And it's a clue to the interesting things about what we're going to talk about. What follows is that there are different perspectives on what's happening here. There's a perspective from our point of view, we're going in for a big black hole. From the point of view of someone outside, we never go in. And that's going to be kind of important for what follows. But there's nothing that's not described by Einstein's theory in that particular bit of the description.
Hang on, let me show you something else that's really cool. This is my privacy dashboard. It shows how many data broke. Why does this? So maybe you. Crucially, they use the code Cleo Abram at the link below and get 60% off an annual plan. Now, back to black holes. So at this moment, we cross the event horizon.
Yeah.
And we don't feel that.
We could have crossed it now.
Just now.
Wouldn't notice.
And our experience now is completely inside the blackness of the black hole from an outsider's perspective.
Yeah.
Gravity is increasing faster and faster. And this is where we get to maybe my favorite word that I have learned in the process of this, which is my understanding of this is when the gravity at your feet is so different from the gravity at your head that you begin to stretch in a very dramatic way. And this is spaghettification.
Yeah.
Could you explain what is happening here?
Yeah. And
as we
you
get
said,
spaghettified.
one way of thinking about it is that another way of thinking about it is just that the distortion in space-time is not constant over the length of your body. Right? So when we're falling in, we might as well be, this is the Einstein's equivalence principle in action, we might as well be in flat space because the distortion, it's like saying on the surface of the Earth, if you look at a square mile of the surface of the Earth, you don't see the curvature, right? You have to go to bigger distances to see that you're on a curved surface. It's kind of like that. So the distortion, the difference in gravitational pull, as you said, or the distortion, you don't feel it until it becomes very distorted. Or there's a big gravitational pull when you get very close to this thing. And then you start to see that, and actually it works. It's not only stretching, it's also a squashing. So the way the tidal gravity works is to squash in one direction and pull in the other direction.
So we are getting...
So you feel it. So you start to feel this strange sort of sensation of being stretched and squashed. and as you go closer and closer to the singularity, those effects become much more extreme until they're so extreme that, first of all, you cease to stay together.
We're one long string of atoms? Yeah, well, what are we now?
And then the atoms get separated, and then the protons, the quarks inside the protons will get separated. And ultimately, according to Einstein's theory, the tidal forces become infinite. So that formally infinite. And so everything is gone. Everything's been ripped apart. And this is what we call the singularity. So the whole thing kind of gets very extreme and breaks down ultimately in Einstein's picture.